So welcome. This is the 8th year of doing Women of Science, and I'll hand it over to Tanya. Go ahead.
So Dr. Caroline Emmanuelle Morisset is a planetary scientist working for the Canadian Space Agency. After completing a PhD at the University of British Columbia, focusing on iron and titanium deposits related to the Proterozoic and Orthosite massifs, Ms. Morisset had the chance to be a postdoctoral fellow at the Canadian Space Agency, the CSA, to study the composition of lunar ilmenite from the Apollo samples and work on potential lunar resources. Afterwards, she worked at Golder Associates as a mining geochemistry consultant. In early 2020, she became a program scientist at the CSA. In that role, her main focus is the scientific aspects of the CSA's lunar program. Thank you.
Thank you very much. So I'll share my screen because I do have slides to share with you, and let me know first, do you hear me well, and do you see my slides? Yes? Okay, perfect.
Yeah.
Okay, excellent. So, well, thank you very much for the invitation. I'm very happy to be here and to take you through basically my journey. And we'll start with how I've become a geologist. Seems on my side, things are slow. Slides are not updating. Okay. So basically, when I was in high school, I really didn't know what to do. And I took those orientation tests that at the time they were providing to everyone. And the results that came out from this test was either I could be a bus driver or brain surgeon. So those were really kind of very bizarre results that I received. And I really didn't know what to do with those, basically. And throughout high school, I know in my times, we had to make choices, even in third year of high school and fourth and fifth, in order if we were being in natural sciences or more social sciences. And because I didn't know what I wanted to do, I always stick with natural sciences in order to not close doors. And basically, when it was time to register to CEGEP, I registered in natural sciences. But I had the opportunity to take a trip to Fiji Island. And that trip was kind of offset with the school year. So it wouldn't, if I was taking the trip, basically, I was not going to start CEGEP because it was overlapping with the autumn. But I decided to do that. And when I came back from that trip, all my friends had started CEGEP. And me, it was kind of middle of the autumn semester. And at that time, I had thought maybe I'll register for January, but I felt pretty much lost. And I decided to not register to CEGEP. And I was, passing time and trying to think what I'm going to do in the future. And I was basically collecting information on all sorts of possibilities. And I remember coming back home with pamphlet about being a florist. And I said, I was saying, well, maybe I could do that. I like flowers. And I also came back with pamphlet about doing jewelry. And I think that one I stick to for a little while, saying, yeah, I really like jewelry. I like stones, maybe it could make a nice life for me. And I remember my father at that time telling me, yes, these are great ideas, but you could do that while you're doing something else as well. And I was like, yeah, whatever, maybe that's the only thing I want to do. But what happened is my father is university professor. So by April, he received the essays from his student. And by looking at him correcting these essays, I got to think, okay, these students, they read in books, because in those years, there was still no internet. So we were all getting the knowledge from books. So they read books, they asked themselves questions, and they wrote it down. So they produced something. And then maybe once they produced it, they felt it was not good enough. So they went back and read books, asked themselves more questions, and wrote it down. And thinking about that process, I remember being, oh, no, I think I do want to do this. I think I do want to go and study and learn more, ask myself questions, and then produce something out of it. So at the end, I registered to CEGEP and still not knowing what I wanted to do. I registered in natural sciences. And what I remember is in my first physics class, I think the prof was naming in what area physics can help. And she talked about geology. And at the time, I wasn't really sure what it was because in high school, I never had a geology introduction. And yeah, so I said, okay, geology, what is that exactly? And asking around, then I got the answer, it's the study of the earth. And that kind of stayed in my head, but it was not until it was time to register to university that I said, okay, what am I going to register into it? And I remembered that. And I said, well, study of the earth, that we must be studying a lot of the volcanoes. And that's always interested me. So I'll go in geology. But I've done that without a pressure of absolutely finishing. I really went with, okay, I'll see if I like it, I'll start it. And like I've said, I thought we would just be talking about volcanoes basically for the whole undergrad. And there I am at my first class of introduction to geology and mineralogy, and we're looking at rocks. And I'm like, why are we doing this? And then I understood, okay, I finally understood, okay, like a volcano, it's in fact molten rocks. And once it's crystallized, it's a rock. And by the second semester, I had a wonderful professor in petrology, which is the science really that studied the rocks. And he made me understand that really a rock is telling the history of the earth, and each rock has a story. And so as historians are telling story over the past hundreds to thousands of years, the rocks and the geologists are in fact building the story of the past billions of years. And then I was lucky enough that my first summer as an undergrad, I got a job as an assistant geologist mapping in James Bay. And it was really a remote location. I put an arrow of the approximate location, but basically we were dropped on the side of a lake by a float plane with the material for construction the camp, but not all even. We were actually taking the trees to do some of the framing for the tents. And it takes about a week and a half to just build the camp before you actually start working as a geologist or an assistant geologist and do mapping of the territory. And that's done by being dropped off one morning on a planned traverse by a helicopter. And then you walk maybe 5 to 8 kilometers during the day. And during that day, during those traverses, what you do is you each time you see outcrops, you describe them, you take notes, and you fight with the bugs as well. That's part of being in James Bay. But really that summer for me, it really was what carried me. And it's really at that point, combining with my first year of geology, I said, oh my God, I just love it. That's what I want to do. So it took me quite a bit of time to find my path, but that summer really did it. And the next summer, I had a quite different job. I worked as an assistant mining geologist at an ilmenite mine near Al Saint-Pierre. And what you see here is the big hole, which has mined already for 50 years, the mineral ilmenite, which I'll discuss just on the next slide. And I started to be quite fascinated with that mineral because you have a picture here of ilmenite, which is a black mineral. And from ilmenite, we're producing a TiO2 pigment, white pigment. So we're actually producing a white pigment out of a black rock. So I always thought that was really fascinating. And that white pigment is opaque, non-flammable, non-toxic. So it's used in all sorts of, it's used in paint. All the white paints that you have TiO2 in it, in plastic, in paper. And since it's not toxic, it's even used in food and cosmetic. And during that summer, I asked question always to the mining geologists about how the deposit was formed. It's that huge mass of ilmenite, and how did it get there, and what are the processes that put it in place. And I could see that the answers were never completely answered, and he had some answers, but he didn't have them all. And then during the course of the summer, we also did mapping around the mine. And we found together a deposit that contained not only ilmenite, but contained rutile, which rutile contains only titanium and oxygen. And rutile is interesting because it's used for extracting titanium metal, which is strong, flexible, and resistant to shock and corrosion. So it's a metal that's often used in aerospace industry and even in medicine, since it's not toxic. A lot of hip replacements are made out of titanium. And so continue on with my questions with this mining geology, I really see that there were holes. And here I'm showing to you a geological map really simplified of southern Quebec. You can see that Montreal is here and Quebec is here. And a geological map, in fact, is what is underneath the grass. So a normal map, you'll see the roads and the village, and you'll see what's above the grass. But now a geological map and a not simplified one will be covered in colors of what it is that we found under the grass. And this one I simplified to highlight the orange ones, which are the anorthosites, which are the massive rocks that do contain the ilmenite deposits. And in the little square, what you see is all the ilmenite deposits that are found within these rocks. And of interest are the two in green, in lozenges, that do contain rutile. So rutile and ilmenite is a rare association. And I've decided to study that in my graduate studies. However, there was nobody in Quebec to study these rocks with. Although we have the highest concentration of these rocks in the world, there was no one that was specialized in those rocks in Quebec. So basically I left for Belgium. And in Belgium, I studied there, and it's not because there's an anorthosite or ilmenite deposit in Belgium, but it's because they studied the Norwegian anorthosite. And here I'm showing you why there's an anorthosite in Norway too. So here you have a paleo map. So a map of about 1 billion years ago. And maybe you've heard of Pangea, which was a supercontinent that happened in the past, but way before Pangea, 1 billion years ago about, there was the supercontinent called Rodinia. And you had Laurentia here, which the south portion here is basically Quebec. And you had Baltica here, which has the Baltic country and a part of Russia. And Norway is just at the tip there. So it was in fact part of the same structure. And so I went to the Norwegian anorthosites while I was in Belgium. And then I started my PhD, still working on these types of deposits. But I went to UBC in Vancouver, and that was really it was really because of the grants. So when I did my PhD at the time, the national, so the NSERC grant, the National Council grants, they could be delivered only if you were registered to a Canadian university for your PhD. They changed since then. Now you're allowed to take your grants with you and study outside Canada. But so my prof in Belgium said, well, wait a minute, I know two people who could really supervise you in Vancouver. One of them was Belgium that went to Vancouver, and the other one was her husband that studied the anorthosite in the US and then was now at UBC. So I left for UBC. And now I'm gonna go through a little bit the method that we use to study rocks and build up a story about geology. So when I started my PhD, the first thing I did is do the mapping. And so what you do is you walk the field. As when you see rocks, you describe what they are, you produce maps of different type of rocks that are present, and you also record where you take the samples. And then when you're back in the lab, there's all sorts of things you do with your samples. And the first thing normally is you will cut them and produce thin section. And I'll show you in the next slide how we use the thin sections. And then we can also do mineral separates, because then we can do the chemical composition of the individual minerals that are present in the rocks. And to do that, we can use heavy liquids. And basically, you can put a rock powder in the liquids, and you can float certain minerals that are lighter and heavier minerals would drown, and you separate them like that. You can also use magnetic separators. So basically, depending on the iron content of your minerals, they'll have a different magnetic susceptibility, and you use magnet, which you can adjust the susceptibility of to separate your mineral phases. And here is what I want to show you of what we can do with thin sections. So on the left, I've put a picture of an outcrop where you can see the ilmenite in black here and the host rock anorthosite, which is more whitish. And on the right, it's an example of the rock, what it looks like when you look at it under the microscope. And this is a sample that must have been taken at the border of both, where there's a bit of mix of both anorthosite and ilmenite deposit together. What you see is the ilmenite in dark here, black. You see the anorthosite, which is in white here, but you see all sorts of minerals that you would not have seen necessarily with your naked eye. You have the beautiful rutile here in red that we've seen earlier on. And in my deposit, the deposit I studied, there was also sapphirine, which takes its name from sapphire, but it's really not as precious, but it's beautiful blue. And we can also look in, now I'm going to show you a picture with looking at ilmenite here, but with an electron microscope. So with an electron microscope, what we're looking at is we bombard basically the sample with electron, and what the results of it is a map of density. And there's phases that are less dense that will be less white, and the denser phase are whitest. So what we could not see on the previous picture, we can see really well with a different type of instrument. And we can use false colors and then do treatment imaging to know the proportion of each phase that were identified. And then other things that we can do is we can do work on the chemistry of the phase. And for that, I had the chance at UBC to have access to incredible labs that we call clean rooms. And why do we work in clean rooms? Well, it's because we want to make sure when we take our minerals and our mineral powder and we put them into solution to analyze them, we want to make sure that the metals we analyze are really the metals that are in our rocks and not the metals that are in the atmosphere. So these rooms are pressure and temperature control and humidity control, and basically they're negative pressure. So when you open the door, the air is coming out. So we're sure that there's no air coming in. And the only air that's coming out is filtered to ensure the quality of the air. And so we do the solution preparation in these kind of environments. And basically we can analyze almost the whole periodic table when we're using a multi-collector, an ICP-MS or mass spectrometer. And here you see the minerals that were put in solution, and then you analyze the solution with those mass spectrometer. And basically you can analyze up to 50 or maybe 70 elements. It's up to how many you want to do. And what we do in geology with these analysis, then we do a kind of graph that what we're looking at is where is the enrichment compared to other elements. And that can tell us the story a little bit of if one rock is enriched similar to another one, it can let us know whether these two rocks have the same origin or not. We also, for these graphs, what is neat is that we normalize them to a norm source. So we can know compared to that source whether we are more enriched or less enriched. And the source we're using, it's either the composition we thought the Earth had at the beginning, or the composition of what we think the solar system had at the beginning. So we know how much we've evolved from that first composition. The other reason to normalize these data, and that's just a fun fact, is that the even elements are much more abundant than the uneven element. And if we wouldn't normalize them, we would just have a crazy zigzag that would be really hard to interpret. So there's two purposes to that normalization. And then something else we can do in those clean lab is to really isolate an element in particular that will allow us to do isotopic measurements, which I'll show you a little later. So how this works is here you have a column for separation, and basically you put the solution that you have your minerals dissolve in, and the column is filled with a resin. And depending on the type of acid and the quantity, some element will stick to the resin and others won't. And that way you can separate the elements you want to analyze from the other element. And then this is basically a chart showing to you how many isotopes they can be for each element. So we've seen the periodic table, which lists all the elements that are present, but isotopes are the same elements. So they have the same protons, but they have different neutrons. So they have slightly different mass for the same element. And we can work with the ratio of these different mass. And for that, we need to be able to measure them, since there are differences, but they're really tiny. You need a really powerful mass spectrometer to be able to differentiate the mass. But basically what we do with those measurements is dating the age of the rocks. So it's like, probably you've heard about the carbon dating. Is the same principle. It's just that we can go to method like uranium lead that allow you to date for rocks that are a billion years old. And we can also use these isotopic ratio as a fingerprint. They like it. So you can know whether the two rocks have the same origin or they have different origin. And so at the end, taking all these data together for my PhD, I was able to determine that the ilmenite and the host anorthosite, they all come from the same magmatic source. And this source was really particular to that moment of Earth 1 billions of years ago when there was rodinia. And there's something really particular about that period of the Earth's evolution that gave rise to these types of rocks. So basically, we built the story that the rocks are contained, but we need to understand it through all different kinds of analysis. So when I finished my PhD, it was end of summer 2008, and I don't know if some of you heard of it, but there was a huge economic crisis in the autumn of 2008. So basically, I finished, I was really happy. I said, I'll go back to Montreal. It was 7 years I was gone, and I had made my decision to come back and to establish in Montreal, and there were absolutely no jobs. So that was a bit a difficult period, a bit discouraging. But what I've done is I went to a mining trade show, and there's a lot of job for geologists. Well, not even at that time, but there's more job for geologists in Abitibi, where there's a lot of gold mines. But there's not so many jobs for geologists in Montreal. And what I've done basically is go through an old phone books I had of mining companies, and go through every company that had an office in Montreal. And I just went to that trade show and gave my CV. And by the biggest luck, I guess, my CV ended up in the hand of the sister of a geologist who was working at the Canadian Space Agency. And when she saw my CV, she said, "Oh my God, ilmenite, anorthosite, we need someone like you to come and study ilmenite on the moon." And I remember I received that email an afternoon, and I just couldn't believe it. I was like, wow, yes, where do I sign it? I want to do this. That's amazing. And we can do a little bit of a geological map just looking at the moon with our naked eye. So you can see that there are whitish part of the moon, and this whitish part, these whitish part are in fact anorthosite. So the same kind of anorthosite where you have so many in southern Quebec. And the darkest part, these are not ilmenite, but these are basaltic rocks that do contain a lot of ilmenite on the moon. So on the moon, the ilmenite is not necessarily associated with the anorthosite like it is on Earth, but it's associated with the basalts. And this is due to the crystallization history of the moon that is much simpler than what happened on Earth. So on the moon, you had a big magma, they called it the magma ocean, and it started to crystallize, and the minerals that form the anorthosite are lighter, so they form a crust, and the ilmenite is denser, and it had a tendency to sink. And when there was a magmatic event that gave the basalts, and by the way, the basalts are the type of rock that we see in volcano like Hawaii. So when there was a volcanic event, they molten the ilmenite and they brought it to the surface. And basically the interest at the time, and it's still an interest today, but you'll see later that now we've made new discoveries with newer interests for extracting resource on the moon. But basically is that we could extract the oxygen that is present in the ilmenite in order to produce oxygen on the moon and to sustain or exploration over there, because a lot of the price to go up and do work on the moon comes from the fact that you need to carry with you everything that you need to survive while you're out there. So so if you can produce part of what you need when you're out there, then it'll be much easier to access the moon and to stay there. So for my postdoc at the agency, I had access to the lunar samples, which I made a request to NASA to have them. But here, just for fun, I want to show you a bit of pictures from Apollo, where you do see the geologists, not the astronauts, sorry, collecting the samples like geologists. And they brought back around 400 kilogram back to Earth through their 6 landed missions. And I had access to 12 of these samples. And here are the pictures. This is a hand sample, so I didn't have access to the whole sample, but I had access to a thin section of the samples. And here is a picture of these, this one of the samples I had access to, again in electron microscopy imaging. And you can see that the ilmenite here is the phase that is the lightest. And then you have, because it's the densest of the phase presented here. And just another example, here is a basalt with big vesicles. And so what happened, we have these same vesicles on Earth. So when the magma reached the surface and it contained gas, it will degas, the gas will escape and it will leave a bubble behind. And we can see we have the same thing happening on Earth and we have the same thing happening on the moon. We think on Earth, that's how the atmosphere formed, by degassing a lot of the gas that were present in the Earth. But on the moon, the gas escaped and it never formed an atmosphere. Yeah, and then when I finished my postdoc, so I spent 3 years at the agency. And there was no position, basically, when I finished my postdoc. There was no permanent position. So I had to choose between 2 jobs, and that was a really difficult decision. I had the possibility to go and study ilmenite again with natural resources of the government of Quebec. They had offered me a 3-year position in my specialty. And then I had an offer from a consultant engineering firm to work as an environmental geochemist. And then I said to myself, so I was a bit afraid of the government position since it was not permanent. And I had just been loving it at the agency and spending 3 years there without the possibility to continue. So I was a bit afraid that that will happen again. And also I had been studying at that time ilmenite for 15 years. And I was afraid if I do another 3 years, that was going to be the only thing I could ever do, because I was already really, really specialized. And I was afraid that it wouldn't be so attractive to employers, because a lot of the work that's done in Quebec is on gold and not on ilmenite. So I've decided to take a jump and go and really change kind of a specialty. And I worked in environmental geochemistry, and I had to learn all about water geochemistry, which I had never touched before. I really worked with the chemistry of the minerals itself, but never with water. And during those times, I worked with all sorts of specialists in geotechnical engineer that these people, they make sure that when you make a pile, it stands and the soil underneath can take it. They make sure that anything that's constructed can hold on. Work with hydrologists that make sure that the water is directed in the right direction and there's no flooding happening on any side. And hydrogeologists that can work really on inputs of water if you have an open pit mine. And all together we were building mines, basically. So I worked there for 7 years, and I've learned also a lot on project management while I was there, like managing budget, managing many people's, managing deadline. So all of these are things that really are helping me today in my new job at CSA. But basically, 2 years ago, there was an opening at CSA. And when I saw this, I wasn't even sure to apply. Well, I didn't hesitate that long because I really love my time at CSA. But what I meant is I was really established in my new job, and I started a junior there, and I was going to be nominated an associate. So I had made my way, and I had a team of 3 people that I had built, that I was supervising. So things were looking well. But I said, I owe it to myself. I loved it so much over there. There's an opportunity. I should just try it. And the process took a whole year, and I had time to really forget about it while it was going on. And basically, when they phoned me, at first I was sure it was to tell me it wasn't me, because it started by saying it's really competitive and it was a long process. I was okay, and then the manager told me, no, but it's you. And I was just, what a shock. And I was so pleased that I said, yeah, for sure, I'm going. So that was a bit more than a little, yeah, that was about a year ago, but I started in January, the time to do the transition properly. And basically, what they told me is that there's 2 program scientists or planetary scientists at CSA, and we have a huge lunar program starting up. So maybe you can take the scientific aspect of the lunar program. So they basically offered me the moon. And I was like, wow, this is amazing. So basically our program, Canada Reaches for the Moon. So we have a program that contains 2 aspects. One aspect of it is to provide the Canadarm to the gateway. So Canadarm3, sorry. So the gateway will be something similar to the International Space Station, but will be orbiting around the moon, and will probably allow more easier access to the moon for astronauts and for lunar exploration. And we also have another program which I worked more actively on, which is the Lunar Exploration Accelerator program. And basically, what that, like we'll see in the next slide, that program, we have $150 million to spend over the 5 next year. And this is really meant to build on our past mission success. So Canada has sent instruments on Mars. We had sent a meteorological station on Phoenix, and we're the first one to analyze snow actually falling on the Martian sky. We have an APXS, which is an instrument that measures the chemical element on the Mars Science Laboratory, which is a rover roving on Mars. And we have a laser altimeter, which I'll talk more at the end of the talk, on the OSIRIS-REx mission. We also have we have developed rovers over the last 18 years with industry. And we're trying to build on all of this in order to better position Canada space sector for future mission, but also within this program to deliver payload on the moon. And what we intend to do over the four to next 5 years is to deliver actually science payload, which can be translated by science instrument on orbiter or on lander at the surface of the moon to take measurements and understand better the lunar resources or other aspect of lunar science. And we also want to have a rover which will contain a US and a Canadian instrument. And as I was working as my postdoc, where all eyes were targeting ilmenite for lunar resources, in around 2010, there was the mission L-Cross, which was basically an orbiter that dropped a projectile on the moon, and the ejecta plume from that projectile, they were able to measure it and measure that they were 4 to 7% of water in that plume. So the first water discovery of the moon was made in about 10 years. And over the last decade, there were numerous studies that are coming out trying to identify really how much water there is, where it is. And it seems to be really concentrated at the poles. But we're still trying to figure out how much water there is out there, and is it enough so that we can produce water from it. But once you have water, it's easy to isolate the oxygen from it to support to support human exploration, basically. And another topic I want to talk just before the end of this talk is the mission OSIRIS-REx, because it's a really exciting time for the mission at this point. So the mission itself is a NASA mission, and it wants to bring back a piece of the asteroid Bennu. And this asteroid is basically what we think is left out of the first cloud of the solar system. So when I said earlier on that we were normalizing our data to the solar system is by analyzing meteorites that we think are representative of what happened when the solar system was first formed. But this would be actually taking a sample of something we think representative of that, but without any contamination from Earth. So it would be the first time we have a similar kind of samples. And the Canadian contribution was to an instrument called a laser altimeter, which is basically shooting a laser beam at the surface, and the time that it takes for the laser to come back, the beam to come back, is representative of the distance. So it can basically do a topographic map of the asteroid, and there was over 3 billion measurements that were taken, and there's not the most detailed map in the history of space exploration that was done, and that was due to a Canadian instrument. And I can show you on the next slide. This is the results of that map. So this is just, for me, it's just amazing. And then what happened 3 weeks ago is that they actually collected the samples successfully. So this is actually the capsule that the sample was collected in, and there was the touch with the asteroid. And what is really exciting about that mission, well, it's all the data that were collected, but it's also because Canada participated, we'll be having 4% of the samples that will be brought back to Earth in 2023. And right now I'm working on how do we need to preserve those samples, and what the whole goal is to have it accessible to the science community for people to study them. And what might be interesting is if one of you, you'll be right in the timing to be in grad school, and it could be one of you that doing the first analysis of these samples. The samples will arrive, like I said, in 2023 in the US, and then they'll stay at NASA for 6 months before they transfer into Canada. So they'll be here in 2024. So I'll just finish with this slide, which I thought is really nice. Dare to explore, follow your curiosity. I think that's my only advice. And don't worry if sometimes you're not too sure where you're gonna go. Follow your heart and your curiosity, and that's it. And I would be happy to take any questions if any.
I'm not sure if, oh, yeah.
So do you want me to turn on my camera?
Yes, please.
Okay. So there's a question, and they're asking how soon we are for running out of ilmenite and anorthosite.
Okay, so that's a good question. It's not, we're not looking at a situation where it's petroleum, let's say, and the resources are almost exhausted, and we've been mining it so much and we're using it so much. So I don't think we're anywhere near a place where we'll be running out of ilmenite. I think the major difficulty here is to find the deposits. So it's more a question of finding them. If you remember the big orange blob, some of the anorthosites are 300 kilometer by 300 kilometers. They're covers in trees, and it's just difficult access to find the resource. So I think that's the major difficulty. But nothing is foreseeable that there'll be a penury of ilmenite.
We just had a comment that says, I really appreciate your description of the Canadian contribution to space exploration and lunar resource mapping. I also love that you are tied to the research into the timing, that you tied the research into the timing that may affect the CEGEP students if they were to pursue this field. Very inspiring.
And it's true. I mean, there's this is the beginning, right? We're participating in, a lot will come out of our LEAP program and our participation into the Gateway. And you're right at the right timing. If you do decide to go into this field, when you'll come out of your undergrads, there'll be great opportunities, I think, for studying this further. And what we're hoping with the OSIRIS-REx samples, we're really hoping that people will build careers on studying those samples, like people have built career on studying the Apollo samples. It's been 15 years the Apollo samples are brought back and people are still making discoveries about them. So we're really hoping it's going to do the same thing with the OSIRIS-REx samples. And we're lucky enough to have a part that will be really much more easy access to Canadians, since it will be here. We do have access to the samples in the US through agreements, but it's not like having them home, basically.
So there's another question. Is there a way that we can create ilmenite or anorthosite with smelting?
That's a good question. I know there is a synthetic rutile, that I know there is. I'm not sure if it's used though. And I mean, what we want to produce, what we use ilmenite for is really for the TiO2 pigment. So I'm not sure if this has been attempted. I would need to look. Because like I said, there's no shortage of it. And I guess it starts to be, those avenues starts to be studies when they can see there's a lack of it. And also the deposits that have been found are kind of easy to mine. They're open pit, so it means that the ore is at the surface. So you just do a hole. It's not like gold, where a lot of mines are underground, and then you start to enter into a whole complexity of mining. So I don't think it's something that has been really studied, because we're still having easy access to it and think that there are still reserves. But it's an interesting question. I'll try to find out more about that.
Okay, and then there's another question too. NASA is planning to build like a lunar settlement in 2024. Is Canada involved in this settlement? Do you know?
So they're planning, I guess, to send back the first woman and the next man on the moon for 2024. And I think the settlement is planned for a bit later on. And there's the whole logistic that's trying to be simplified by having the gateway and then by finding resource on the surface. So we are part of it, as in our LEAP program. We're trying to, there's a good chance, like the scientific question and the science goals are still to be determined based on the instrument that will flow, but that will fly there. But there are a good chances that we'll participate into trying to find resources, as it is one of the hot topics right now, and we'll be involved in that way. And the goal of Canada, there's a Canadian space strategy that has been published, and a long-term goal for Canada would be to send astronauts to the moon as well. And that might be a good job for you as well. That might be a good timing for the Vanier CEGEP student.
There's another question, and what about private companies like Blue Origin in lunar exploration?
Yeah, so NASA has invested a lot in a program called Eclipse, which is a commercial program, and a commercial lander, basically, that are going to be sending a lot of payloads to the moon. And we actually, the science instrument we're going to be sending through either on lander or a rover, or is going to fly through this program. Now, within this program, it's not certain which company will be selected for which flight. This is still to come for the future. But the intention now is that the Canadian payload will be fly through a commercial lander sponsored by NASA.
Oh, okay, another question. If water is so rare in the universe, and is water, okay, if water is so rare in the universe, and is it created by magma cooling?
That is the I don't know how many billion question. that is one of, and that is also a part of the science that I know less, that I know it's an outcome of the OSIRIS-REx, because there might be some element there that can give us answer on what is primordial water and where does it came from. So we know there's water in certain comets and in certain asteroids. Did water come and form from degassing the Earth, or did water come from a comet? These are all incredible questions that people will spend their careers, I think, finding out. And hopefully, the more we have samples, the more we explore, the closer we are to have an answer to that question.
Okay, somebody says that they are going to write a project about Artemis 2024, the lunar exploration, and that this presentation was very helpful for them, and it allowed them to see Canada's role in the space and the moon.
Excellent, and don't hesitate. I wanted to have a page at the end, and I'm sorry I didn't have time to do it, with links for further resources, but you can go to the CSA website, just look at it on Google, look at the NASA website. There's also the Lunar Planetary Institute that you can Google, and there's tons and tons of data and information available. And what I'm finding as well is that on YouTube, there are recorded class that you can follow, and these can be like so interesting. So sometimes at night, that's what I do. I sit down in front of a YouTube class and I just listen to what is being taught, and it's a good way to learn. So there's really a lot of information available on the web, but you can start by the CSA website, NASA website, and the Lunar Planetary Institute website. These are good resources to find information.
Okay, so there's two questions. The first one is, does CSA have educational outreach programs for students?
Yes, yes, they do. And I haven't been here long enough, but I know there are some CSA online. I don't know if they could answer to this. Or maybe what we could do is we could follow up with this information on an email.
Yes, absolutely. You can send me those links and I'll get them distributed somehow in some way.
Okay, perfect.
Yeah.
Okay.
And then there was a second question. How old are the ilmenite and anorthosite deposits?
So they're about 1.055 billion year. So 1,005. Yeah, sorry. I stick to 1.055 billion years. I'll stick to say it that way. So all around about a billion year old. And it is really particular because the time spent on Earth is a bit larger than that. It goes from 2 billion to maybe 900 million. but there's really a concentration only in this time of the Earth, and there's nothing else like that in terms of rock type, where other rock types have been seen throughout the history of the Earth. So they're really talking about the one moment in the evolution of our planet, and probably the composition of the mantle of the Earth at that time. They're really a witness of that.
And a follow-up to that question is, what process in the magma made that happen?
That's it. So that's a really great question. So I'll try to explain this fast. But what happened basically, these rock types, what we think why they are really related in that time slot is because you need to form a crust that is thick enough to have magma that enters the crust and doesn't erupt. If the crust is too thin, it will just do volcanoes. And if you have rocks that are too thick, then it won't produce the same type of magma at the same level. And so we think at that time of the Earth, the crust was just the right level, and you had a magma, which is still debatable on why it had the right composition at that time. It still needs to be proven. But basically what happened is you have magma from the mantle that got stuck at the limit of the crust and the mantle and started to crystallize there. And a little bit like on the moon, the minerals making the anorthosite that are lighter got rise through that crust, and then follow a little bit of liquid with it. And since there's no iron in the anorthosite part, all the iron was left out to produce the ilmenite. So I hope I'm not losing you, but it's really a complexity of various elements that played together to result into these deposits. But what is really clear, and what necessarily clear, is that there's a real link between the ilmenite deposit and the anorthosite, and it's really because of the way the anorthosite formed that we found the ilmenite with it.
Another follow-up is, does the moon have more of these deposits than the Earth?
More what? More what deposit?
Does the moon have more of these deposits than the Earth?
Of the ilmenite deposit? It's different on the moon. It's because we haven't found so far concentration of 100% ilmenite like we have on Earth. So what we do have on the moon is that the basalts it can contain up to 12% ilmenite, as on Earth it contains only 2 or 3% ilmenite. So it's a bit hard to make a one-on-one comparison, and I've never made the calculation whether the amount of ilmenite is equivalent of or more, which is actually quite an interesting question. It would be interesting to know. But it is certainly a bit different. So a straight comparison cannot be done just like that. I think we need to calculate how much could be on the moon, and then we could answer. But we don't necessarily have all the data on the moon to know really what's the real distribution, as we have samples from only 6 different places on the moon. It's hard to make extrapolations basically based on this. So there's still a lot more to discover on the moon.
I don't have any more questions coming in at the moment.
Okay. Well, thank you so much. I was really happy to be here. I was happy with the questions, and I'll send out the links and the additional information for a follow-up.
Thank you very much, Dr. Morisset, and everyone. I please encourage you to write something down in the chat that you will take away from this talk that you'll think about for the day to come. And we are very grateful for you spending time with us and showing us all the work that it takes. It's certainly inspiring to me.
Excellent. Thank you. Thank you.